Kia ora koutou, welcome back to this video. We're looking at molecules, bonding and structure, this time part 3. So getting on with it. In the last videos we looked at molecules, what they were, non-atoms bonded to non-atoms, and that they were covalent bonds. And we looked at Lewis diagrams, which were how we would visualize how those molecules look, where those bonds are. So we've done some examples of some Lewis diagrams there. In this video, we're going to look at what these molecules look like in 3D space. So here we've just drawn 2D versions of them, so they will just look completely flat on the page. But what actually happens is that these electrons, because they have negative charges, so the electrons, these are regions of negative charge there, and we know that um, like repels like. So if we've got regions of negative charge here, they're going to separate as much as they can in space. And so because space isn't 2D, they've got more space to move into. This methane molecule is not actually going to look quite like this. It's not going to be flat on the page. Um, so we can look at how that will look in space. So if you want to, you can do this yourself. So you can Google PHET molecule shapes, and then click on this molecule shapes PHET there. This is a great animation showing what the molecules look like. Hope this loads quickly. There we go. So we've got a model here. Um, so what we can do is we'll include the names there. So this is a molecule that's got it's got one central atom and two atoms around the outsides of it. We can just click here and add in some more bonds. So this would be a representation um, of the methane molecule that we did before. So if that was in the middle, that we would say that is carbon, and these are all hydrogen there. So you can see it's not actually flat. They repel as much as they can, so they repel for maximum separation into into this shape here. If we were to look at, for example, another one that we did, uh, carbon dioxide, we could look at carbon dioxide and see how that C with two double bonds to oxygens would look like. So we'll get rid of all of those single bonds and we'll put in two double bonds. And see they're repelling as much as they can, these regions here, and that looks slightly different. So that is a linear shape. Let's see what. And we'll look at another one that we've done. Let's do this beryllium dichloride, or maybe actually we'll do this boron trichloride. We'll see what that looks like in space. So we don't have any double bonds. We've got three single bonds. So this would be what that boron trichloride looks like. So it's within 3D space, these regions of negative charge will repel as much as they can, so they get the maximum separation. There are different shapes that we need to know for this topic. So in an exam, you might be given chemical formula. You would then need to draw the Lewis diagram of that chemical, of that molecule, and then you would need to describe what the shape of the molecule will look like. So what we're going to do in this video is go over all the possible shapes that you would need to know for molecules. So to go over those shapes, we will go through a bit of a table here. So this would be, if you're writing down some notes, this would be a good table to draw into your notes as we go along, and it'll give you something to reference as you're doing some practice questions or practice exams later. So there can be regions of negative charge that will either be electrons. So if you see a pair of electrons, that is a region of negative charge, or a bond. And so the bond could be a single bond or a double bond. It's still just one region of negative charge. So regions of negative charge are either a pair of electrons or a bond region. electrons. So in this case, we're going to have, we'll start with 4. So if we've got 4 regions of negative charge, bonding regions. So this is anytime there's a single or a double bond. We'll give an example of, we'll say there's 4 bonding regions. So an example of a molecule that has 4 regions of negative charge and 4 bonding regions is one that we've just looked at before, is methane. So CH4. So we'll look at CH4 back in the shapes thing that we were doing before. So we've got 3. So we've got 4 single bonds here. So carbon would be in the middle, hydrogens are on the outside. The name of this shape is called a tetrahedral shape. So when you've got one central atom, 4 regions of negative charge, and all 4 of those regions of negative charge are bonding regions, that is what is called a tetrahedral shape. So the name of this shape is a tetrahedral. So it's tetrahedral like that. The angle for this molecule we can see is 109.5 0.5 degrees. What we need to write there is just 109 degrees. That's fine for our level 2 chemistry. So we'd go 109 degrees. Do I have a degrees sign? I'm not sure. We'll just say 109. And then there's a way that we can draw what this methane looks like. So I might do we'll do one more column, and we'll call that shape. So this is when we're drawing the shape of it, we need to show on our piece of paper what the molecule would look like. So to do that, we'll draw the central atom, and then we draw with a line that is telling us that this bond angle is coming out on the same plane as the page. So this carbon is bonded to these 2 hydrogens, which are on the same plane as the page. If I draw a wedge like this is to indicate that there's a hydrogen that's coming out. So there's a hydrogen coming out of the page towards us. And then if we draw like a Wi-Fi symbol there, that shows that the bond is going into the page. So we'll have a look back at the simulation, and I'll show you, we'll orientate this molecule to show you what I mean. So it would be something like, so yeah, I'm drawing it like this. So you can see that this carbon is bonded to the hydrogen there. That's going up and down on the same plane as this one here. So if we had the page like that, this hydrogen back here, that's going back into the page, and this hydrogen here is coming out towards it. So I've shown that shape where we don't have the simulation to be able to do it. I've shown it just on the whiteboard here with the wedge showing the hydrogen coming towards us, and the dotted line showing the hydrogen going back into the page. Okay, so we'll look at, so that's an example of a molecule that has 4 bonding regions and 4 regions of negative charge. So we'll look at another one, another example that has 4 regions of negative charge and 3 bonding regions. So an example of a molecule that has 4 regions of negative charge and 3 bonding regions is ammonia. So ammonia was NH3. We've gone over ammonia before in the previous video. That was bonding and structure part 1. We'll just quickly draw what that looks like. So nitrogen has got 5 valence electrons, 4, 5, and we're bonding that to 3 hydrogens. So hydrogen there, hydrogen here, and hydrogen here. So you can see nitrogen is bonded to those 3 hydrogens, and the nitrogen has got 8 electrons, so that has got a full outer shell, that's fine, and then each hydrogen has got 2 electrons, which fill up its outer shell, and there's one region of just paired electrons there. That's a lone pair of electrons, and there are 3 bonding regions. Each bonding region still counts towards a region of negative charge though, so that's why in total we have 1, 2, 3, we have 4 regions of negative charge, but only 3 of those regions are bonding. So that's why we've said that there's those 4 regions of negative charge, 3 bonding regions in ammonia. So we'll show using our simulation what that would look like. So we've got those 3 bonding regions and then a lone pair of electrons. So you can see it looks like this. So the regions of negative charge, they still repel for maximum separation. So you can see that the angle here, which was 109.5 degrees, that has stayed the same even though there's one less bonding region. That's because it's the regions of negative charge that repel, not just the bonding regions. So the electrons still repel into that tetrahedral shape, but what we say with this one is that we only talk about the overall shape of the parts of it that we of the bonding regions of this molecule. So the actual molecule geometry is called a trigonal pyramidal or a trigonal pyramid. So we'll go back to our whiteboard and complete the table. So the name of this shape for ammonia is trigonal pyramid. And we'll notice that the bond angle for it was still that 109.5, or we can just write 109 degrees. So the angle between the bonds was 109, and the shape, when we're drawing the shape, we don't actually, if there's lone electrons, we don't actually need to draw the lone electrons. You can, you wouldn't be marked down for it, but you don't need to if you're showing the shape. So we'll have nitrogen there. We have a nitrogen coming, a hydrogen bonded to that nitrogen like that. And then we've got a hydrogen coming out towards the page and one hydrogen going back towards the page. So we just need to learn, we can figure out how to do these on the spot, but it's best if we just get some practice of drawing these shapes. I'm just going to draw the 2 electrons in there anyway, just for good practice. We just need to practice how to draw these shapes with the wedges and those dashed lines. So the next one, we'll just move right through this. So if we had 4 regions of negative charge and 2 bonding regions, 4 regions of negative charge, 2 bonding regions. An example of that is, so when you have an exam, you'll be given the molecule first, and you'll need to work out how many bonding regions or regions of negative charge there are. But an example of that would be sulfur difluoride, so SF2. So we will first of all draw the Lewis structure for that. Sorry, I haven't set a column aside for doing the Lewis structure for this, but so this might get a little bit messy. But sulfur has, we'll look at the periodic table to work out how many electrons that sulfur has in its outer shell. So sulfur, we can see it underneath oxygen there, so it's got an atomic number of 16. So that means it's got 16 electrons. So 2 in the first shell, 8 in the second, and then 6 electrons in the third shell. So we can draw the electrons around sulfur, draw it like that. And the fluoride has got 7 electrons. It's in group 17, so we know it's got 7 electrons in its outer shell. 4, 5, 6, 7. And then this fluorine has got 1, 2, 3, 4, 5, 6, 7. So sulfur difluoride looks like this. We've got the 1, 2, 3, 4 regions of negative charge, and 2 of those regions are involved in bonding. So we've got 4 regions of negative charge, 2 bonding regions. That's exactly what we've shown there, 4 regions of negative charge, 2 bonding regions. What is the shape of this going to be? So we'll look back at our simulation, take away one of those and one of those. 4 regions of negative charge, 2 bonding regions. we can see that the molecule geometry, so this one is what we call a bent shape. So if we look at it on the page like that, you can just see that it's not completely linear. This is a bent shape, and the regions of negative charge, they still hold that tetrahedral geometry. So the regions of negative charge are still 109 degrees, the bond angle is still 109 degrees, but the actual shape of this molecule is a bent shape. So the name of the shape is bent. The angle is 109 degrees, and we would draw that shape like this. The sulfur, if we can just go fluorine, we can draw the electrons around there like that. So I've drawn this shape. The fluorines are on the same plane as the page, and that is because we can move this molecule around in a way that those are on the same plane as the page. And then these electrons, we don't need to show whether they're coming out or going back into the page, so we can just draw them around around the central atom. So that is the SF2 molecule. We'll now move into, so we've done 3 examples so far, and they all include 3 regions of negative charge. We'll now move into some examples that have, those 3 examples that have 4 regions of negative charge. We'll now move into some examples that have 3 regions of negative charge. So if we say we've got 3 regions of negative charge, and all 3 of those regions are bonding regions, an example of that will be one that we've already gone over, so beryllium trichloride. We'll go back to the Lewis diagram that we've done previously. We can see that there's those 6 electrons around the boron atom involved in bonding, and the chlorines are around it like that. So we'll go back into the simulation. We've got, take away all of the lone pairs. We've got 3 bonding regions and 3 regions of negative charge, so it looks like this. So we can see that it's no longer, the bond angle has changed, and it is now 120 degrees. And all of these bonds are on the same plane. So that will help us when we're drawing out what this shape looks like on the page. So we've given here what the name of the molecule is. So this is a trigonal planar molecule, and the regions of negative charge repel into a trigonal planar shape as well, with a bond angle of 120 degrees. So we'll continue that on our table. Beryllium trichloride. This is a trigonal planar shape. Trigonal planar, and the bond angle of it is 120 degrees. So notice how as soon as the number of regions of negative charge has changed, the bond angle has changed. So it's actually only for the purposes that we're using this, it's actually only the regions of negative charge that affect the bond angle. It's not actually the bonding regions. So if you ever see that there's 4 regions of negative charge, the bond angle is going to be 109 degrees. If there are 3 regions of negative charge, then the bond angle is always going to be 120. And so we can draw this shape just by going boron, and then we can have 3 chlorines coming out like this. We don't need to draw any of these chlorines going into the page or coming out of the page, because it just looks, this is what it looks like, that we can show them all on the same plane. So that's relatively easy. Okay, so we'll look at an example of a molecule that has 3 regions of negative charge and two bonding regions. So the example that we're going to look at for this is sulfur dioxide. So sulfur dioxide, so 2. This one is actually quite a tricky one. So we'll show the Lewis diagram for this. I'll just do this under, I'll do this to the left. So sulfur has, we've seen just before that it has those 6 electrons, those 6 valence electrons, 1, 2, 3, 4, 5, 6. Oxygen has also got 1, 2, 3, 4, 5, 6. So we can't really use the rules that we were using before, which were to work out which atom went as the central atom. We would count up the number of lone electrons in the valence shell of that atom. In this case, they both have 2 lone electrons, so we don't know which one would go into the center. So we just need to memorize the sulfur dioxide. So in this case, sulfur is going to go into the middle, and we are going to have an oxygen, 2 oxygens on the outside of it, 1, 2, 3, 4, and oh, excuse me. So there's going to be, sulfur actually has 2 electrons there, and the oxygen atoms, one oxygen atom forms a double bond with the sulfur, and the other oxygen atom forms a single bond with the sulfur. This is how we show this molecule. So this is one, it's quite hard to work out. You just need to memorize this one. So there's really 3 exceptions that you need to think of. Well, with Lewis diagrams, there's that boron trichloride, beryllium dichloride, and sulfur dioxide. If we just remember how to draw this, just give this some practice, the number of electrons all add up to the total number of valence electrons. So this works. So this is sulfur dioxide. We can see that we have 1, 2, 3 regions of negative charge, and 2 of these regions are bonding regions. So it doesn't matter that this is a double bond, that still counts as one bonding region. So we'll show this on our simulator. We've got 1 single bond and 1 double bond, and we also have a lone pair of electrons. So these, we can still see that because there's 3 regions of negative charge, we still have that 120-degree angle there. But the overall, the shape of the molecule is bent. So it's similar again to what we had before. It's a bent shape. It's just that the difference between the previous bent shape that we looked at, which had a bond angle of 109 degrees. So this one, this sulfur difluoride, had a bond angle of 109 degrees. This one has the same, the shape is still called the same, bent, but the bond angle, because there's only 3 regions of negative charge, the bond angle is 109 degrees. So 109, like this. And we'll draw that out. So this one goes there. For this one, we've got sulfur. That would be showing the bent shape that we've looked at here. Okay, so that is 3 regions of negative charge. We'll now look at one example with 2 regions of negative charge and 2 bonding regions. So an example of this we've looked at already is carbon dioxide. So carbon dioxide, we'll go back to what our Lewis structure was. We can see we've got those 2 double bonds, so 2 regions of negative charge and 2 bonding regions. And then we have the oxygen atoms are on the outside of it. So we'll do this as a simulation. We'll get rid of that and that. Add in another double bond. And so we can see that these repel, and these oxygen atoms are opposite each other around that carbon atom. And so the name of this is linear, and the electron geometry is the same. The electron geometry is linear as well, and it has a bond angle of 180 degrees. So we'll complete that in our table. carbon dioxide, this shape is called linear, and has a bond angle of 180. Oh, I've made a mistake here. That should be 120, shouldn't it? So that should have been 120, so apologies if that put anyone off. And then this carbon dioxide has a bond angle of 180 degrees. And we would draw that by just showing the carbon double bonded to oxygen. And that's all on the same plane, so we don't need to use any wedges or any dashed lines. And those are all of the shapes that we will need to remember. So to be able to do these, draw out this table as neat as you can and refer back to it. And then it's just a matter of practice to be able to get used to the names of the shapes and the bond angles and being able to draw the shapes of those molecules. So thanks for watching this video. Like and subscribe for some more superb chemistry videos, and I'll see you for the next video.